if you have a graphing calculator, we're going to use it to graph some of these trig graphs. But if you don't have it, it's just a learning process of how things are. Because again, like some schools will not allow you to use the graphing calculator, and they anticipate that you can learn how to graph without the calculator. But the calculator, as you can imagine, is a big help. That's not what I want to do. This is what I want to do. Okay, so the business, if you ever miss the very beginning of class, you miss where we go over things, just a quick business part of what's due, assignments and all, and where we are in the course. So we're just completing the second week, and we have covered, all about angles being measured in degrees and radians, and we've studied arc length, the length of the arc, and standard angles, the unit circle, and the trig tables, the trig chart of the trig table. And then on Tuesday, we covered the sine and cosine functions, and we covered area of a sector. Okay, still learning. Brandon, are you Brandon? Okay. Sorry if it seems like I'm a slow learner, but I do have a lot of classes. Okay, but I'm learning. Okay. And so today we're going to talk about how to graph the sine and cosine function. And if you have a graphing calculator, I'm going to show you how to do it with that. But we're also going to need to know, we can't be calculator dependent and only know how to do it. We've got to know how to do it both ways if possible. Okay, so that's where we are. Then next week we'll be going, we've got Tuesdays and Thursday, we'll be doing we're going to talk about the other 4 trig functions, the tan, cotan, secant, and cosecant. And then on Thursday, we'll talk about the graphs. And that will finish us up. Now, that is not the end of chapter 5, but it is a good stopping point for us to then stop and have a test on chapter 5. So anticipate we're going to have a review on Tuesday, and then the chapter test will be that week. We'll be in the 4th week, and we'll be taking that test online. It will be through some type of proctoring, either HonorLock or with Lockdown Browser, but it will allow us to take our test outside of class. So that Tuesday, a couple of weeks from now, well, really it's less than 2 weeks, we'll be reviewing what we've gone over in sections 1, 2, 3, and 4. Then after that, we're going to go into triangles. We're going to study all kinds of solving different triangles, whether they're right triangles we'll start with, but then we'll go into non-right triangles and know how and learn applications of solving all the different triangles. Okay, so what do we have though coming up right now? If you need to go to modules because that's where it lists things. And when I go to modules, as you see in week 2, we've got a quiz that's going to be due this coming Tuesday night. And with all the quizzes and tests, you're going to have a window of time to do it on your own outside of class. So it's already open. You can take it now. What does it cover? I always put up above it. These are the things, these are the topics that are going to be on this 5-question quiz. It's multiple choice, but you do need to take it before the end, before February the 3rd starts. All right, now coming up, we do have homeworks. We still have these homeworks. So from the 1st, we had the homework. Everything is due about the time that the test will be due. the chapter test. So we've got angles and degrees, and we've got sine and cosine, and we've got our sine and cosine graphs. And then what we'll finish up will be the tangent, the cotangent, secant, and cosecant, again, due when the test is due. So don't be forgetting about that. Now, next week, we're going to have another quiz. It will be due on the 9th, and it involves the sine, the cosine, negative angles, and terminal point, which we've already discussed. So you should, really, you could take that now, but don't forget to do all that. So let's go ahead and get started with our lecture today on these different, we're just going to focus on the sine and the cosine. And they're used in a lot of applications because they look identical, but they're not tracking through the same ordered pairs. But one is shifted over to the left of the other, but they're both waves. And so those waves have a lot of applications because a lot of things are waves, not just water having waves, but you have your sound waves and all kinds of other, radio waves and microwaves, and they all have a wave. And the difference between those waves would be what we're going to learn words like amplitude, that's like how high do they go, and then period, that's how close they are together before it repeats itself, and frequency, the frequency of a wave. So these are concepts that we're going to look at today. So not just in the graphing, but in the understanding of the term. So one of the things that's going to happen that when we go to graph these trig functions, the x-axis will be subdivided. The little markations that you see, they're subdivided based on radian units. So that corresponds to angles. The angles were measured in radians, and so the x-axis is going to correlate to the angle, and it is subdivided that way. Now, it can go, if you go this way, it's actually going in a negative direction, and you'll have like negative pi over 2, negative pi, negative 3 pi over 2, negative 2 pi. If you go in this direction, you see it's increasing, and it's the angles inside in your trig chart and your unit circle. But it keeps on going. So it just keeps growing. And that's where you get into those larger angles that represent more than one revolution around the unit circle. So the next would be 2 pi plus pi over 2, which is, it's like 2 plus 1/2, which is 2.5, which is 5 pi over 2. And then 3 pi, and then 7 pi over 2, and then 4 pi. So it just keeps getting larger. So what they're doing right here is they're just making a small snapshot of a wave, but that wave keeps going infinitely to the right and infinitely to the left. Now, how high this goes comes off of the unit circle. And so what it's really doing is it's the sine curve. You can think of your input along the x-axis as your angle, but the y-coordinate, or how high this goes, comes off the y-coordinates along each point in the unit circle. So remember, the sine graph is the y-coordinates of each of those terminal points. So for each angle, it's graphing just the y-coordinate. So if I were to look at my trig table, or I were to look at the unit circle for each angle, it's going to graph just that y coordinate of the terminal point there. That's your sine curve. So at the origin, when the angle's 0, the sine value, the y coordinate was 0, right? And then you kept doing these values until you got up here. Now this was the angle pi over 2, 90 degrees pi over 2. The y coordinate here, this is the ordered pair 0, 1. So the y coordinate at pi over 2 was 1. So when they graphed it, they said when the angle's pi over 2, the y coordinate is 1. So that's how they're getting these points. Now, if you were to come over to here, when the angle's pi, the y coordinate there was 0, because this was the ordered pair negative 1, 0. So they graphed the y coordinate, and so at pi you are at 0. Now when you come down to 3 pi over 2, that terminal point there would be what? 0, negative 1. The sine grabs the negative 1, the y coordinate, and so when you're at 3 pi over 2, the y coordinate was negative 1. So what they did is they graphed all the y coordinates aligned to the angles as you went around. When you came back to here, you're coming back to the same point that you started at. So we're going to be looking at the concept of amplitude, like how high does this go? What is the distance here? We're going to be looking at the period. The period is how long does this take before the graph repeats itself? And it's going to start repeating itself right there, because it'll start repeating the same curve, the up and the down that you see. So it'll start to go up and then go down, and they'll be back again. So that is your sine. So your basic sine curve is taking the values off the unit circle. But now let's look at how can I use the calculator to graph this for me. So the first thing you want to do, just like before, we said when you want to put in an angle, you have to indicate whether you're putting in the angle is it measured in degrees, is it measured in radians? But to graph a trig function, you need to be in radians. Not negotiable there. To graph a trig function, the mode needs to be in radians. Okay, so how do I set it in radians? Right here. I'm just going to come into mode, and I'm going to go over and make sure that it's in radians. If it's in degrees, remember I said that a lot of times you're going to be in degrees, and then you go do something, you need to be in radians, and then you go back to put in an angle, and you say, what is the sine of 41 degrees? And you get the wrong answer, and you're like, what? And I'm like, are you in degree mode? So you're going to find you're switching back and forth between degrees and radians, So always check before when you pick up the calculator and start to do work on it. Are you in the right mode for what you want to do? Okay, so now that I've made sure I'm in radians, one of the other things that you would like to do, you don't have to, but this is nice, that you can align that x-axis to be divided up into pi over 2 and pi and 3 pi over 2 and 2 pi by, instead of being what is normal, the normal thing you're normally in is you go zoom, and then it'll bring up this submenu, and normally you're in standard, zoom 6. But when you go to graph a trig function, you might want to be instead in zoom trig number 7. And you can either type, once you hit zoom, you can either type in the number 7, you can either hit 7 on the keyboard, or you can arrow down with the down arrow and then hit enter on that. You can do it either way, but the quick way is just to actually hit the 7 key, and it will put you in that. Okay, so now I will tell you the rest of the way when you say I wanted to graph the sine of your angle, whatever if it's just the sine of x or the sine of theta. Then I would go to the y equals key, and I would click on y equals, and then I would say, I'm going to graph the sine, and I would hit sine. And then you've got to say your angle. Now, whether if it's just an x or just a theta, then all you do is, this is your variable key, and you'll hit that. So I'll hit sine, and then I'll hit my variable key, and it's going to put your answer as x, but don't worry about that. If you're, maybe your problem said theta, but that doesn't matter, because it's going to graph the sine of x, and that's what you want. And then I just hit graph. So my graph is up here, and what you should get is your sine curve. Now, if you're in Zoom Trig, it kind of zooms in, but it also is going to align. It's also going to align you should get this graph, but it should continue on, and it'll continue on that way. Are you getting something that looked like a sine wave that goes through the origin? Okay. So I've got my sine curve there. Now, it's really important to know this. Now, one of the things about your basic sine curve, how high it's going to go should only be up, if it's just the sine of x, it's only going to go up to a +1. And this is why the Zoom Trig helps, because it's kind of zooming in. If you were in standard mode going up to 1, it would almost look like a little slight wave, but it almost would look flat. So it's going to go up to 1, and then cross down, and then go down to -1, and then cross back. That's your basic sine curve. But again, the wave keeps going to the right and to the left. All right, so that's how you are going to graph your sine curve. If it's just the basic sine of x. So let's talk about our sine curve a little bit more. We want to talk about the characteristics of it. And anytime that you are studying functions, there are topics that would come up, and you've heard it before. I'm sure you've heard, maybe even felt tortured by the concept of domain and range, but now, and y-intercept. But now we're going to bring in a new word, which is called period. And we're also going to be bringing in another word called magnitude. But so what I was saying is, what they did, this is coming from now the trig table as opposed to the unit circle. They're just displaying the same information in a different format. This is how they graphed the trig, the basic sine of x, your base graph. So this is my input value. It's considered to be the x. The x is the angle. So it's graphing these as ordered pairs. So it's going to graph the ordered pair, 0, 0. Now, pi/6, if you were to think of, since this is divided in radians, pi/6 is about here. And then you've got pi/4, which is halfway, and then pi/3, and then you get to pi/2. So it's actually graphing these points. So this would be right here where it's at 1/2. This would be the angle pi/6, 1/2. Now, these values, if you converted it to a decimal, they're going to be, these two values will be somewhere a little more than 0.5, but less than 1. So it's increasing. Then notice it's going to start doing what? It's going to start going back smaller. And notice these values are symmetrical. So this will be symmetrical here, not to the y-axis, but just symmetrical along this line, these two values. Then it crosses the x-axis at 0, where the angle is pi. Notice now you're going to start going down below the x-axis. These are negative values. and the lowest it goes down to is a negative 1 at 3 power 2. Then notice it symmetrically starts rising again until it gets back to 0. So if I wanted to think in terms of y-intercept, it's a function. The sine curve is a function. So it's only going to have one point where it crosses the y-axis, and that would be at the origin. So you got one y-intercept. But now your x-intercepts, very, very many. And I think you remember from pre-cal algebra, you were asked to find the zeros of a polynomial. Those were your x-intercepts. Well, unlike those polynomials where you maybe only had 1 or 2 or 3 or 4, there's an infinite number of x-intercepts, but it's always the same distance apart. Notice it's an equal distance apart. So it's predictable what the sine curve, it's a sine wave, is going to look like. So notice every pi units, so 0, pi, 2 pi, 3 pi, 4 pi, the y-coordinate is 0. And that's why like in like the class, some of the classes that I'm teaching, we oftentimes have to calculate what is the sine at 2 pi? What is the sine at 4 pi? I don't even have to look it up. If it's the sine of 0 or pi or 2 pi or 3 pi or 4 pi, the answer is 0 because those are the x-intercepts. Now, some other things. Let's talk about domain. Domain, if we just think about a function as a machine, like the Coke machine down the hall, the domain would be what can I input in it and the machine accepts it and doesn't spit it out. So if I were to go down the hall, could I put pennies in it? No, it's not made for pennies. So pennies not in the domain. So the domain for that Coke machine is what am I allowed to put in? It accepts dollars. I wouldn't put $100 bill in it because I think you're going to lose your money. It accepts quarters, nickels, and dimes, and that's it. So the domain is what I can input in that it accepts and doesn't, and then will give you the product you want. So if we think of domain as what values can I input in for angles, really the only, you think about it, is there an X value that I could plug in, get an undefined situation? And so I'll ask you, as you graph it, is this a continuous curve? It is a continuous curve. So it really means that there isn't going to be any values for angles that I would sub into the sine curve and get an undefined. And that's going to be true with the cosine. I can plug in any value, any angle, and I'm going to be able to get an answer. So if I asked with my calculator, I said, what is the sine, say, and I give it an angle, it's going to give me an answer. It won't say error, domain error. Now, that is not going to be true with the tangent and the cotangent and the secant and the cosecant, because they have values. They're defined as a fraction, and there are values that make the denominator 0. And so they're not continuous curves. They're going to have places where they stop and then start back again. But your sine curve is a continuous curve. And so I can input in the domain as all real numbers, any angle I want to put in. Now the range is looking at the graph and say, how high does it go and how low does it go? In other words, tell me the y values. Is there a maximum y value that it goes up to and then turns around and comes back down? Yep. So how high does the graph go? Well, it goes all the way up to 1. It includes 1, so it has a bracket. And then it goes down, 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 down. But then what does it do? It gets to a -1, includes a -1, has a a solid circle, and then it goes back up. So it goes only in between a -1 and 1, and I'm talking about your standard basic sine curve. There are going to be some things we can do to make that curve go higher, to increase the domain, we can increase the range. Now, period, that's going to come in over and over again. The different trig functions have different periods, but the period means how long before the graph repeats the exact same shape. It's the horizontal distance. So notice in red, this is a unique piece. And then after that, it does what? It just starts to repeat the same shape. In other words, it just goes around the unit circle, what, one time. So what is the length of the unit circle? 2 pi. So it took 2 pi to go through all the values. So the period is the horizontal distance before the graph starts repeating the same shape over again. That's just in common everyday language. That's what it is. So that's your basic sine graph. So amplitude. Another way, sometimes the graphs, they'll show the period as the distance between the two high points. So, here is one period, but you could think it's the distance between the two high points, which is still 2 pi. Now, amplitude is how high, what is the distance here? This gets into when you're talking about radio waves and microwaves and all those other waves, all sound waves, there's an amplitude to it. Now, it's always the distance between the middle up, which is equal to the middle down. So it's not the distance from the lowest to the highest. It's only the distance from the middle to the top, which would be equal to the middle down. So it's only the amplitude of this is exactly the same as this, because these are, the middle cuts through the middle. So the amplitude of the basic sine curve is 1 unit. The amplitude of the basic sine curve is 1 unit. It's the height of the wave. It's basically, to think about it that way. And I'm sure some of you can think of a lot of applications. If they're, if you even talk about going out boating and stuff, you kind of need to know, how high are the waves going out there? Because many a person has lost their life going out on Mobile Bay and they weren't paying attention to the weather. And before they knew it, their boat got swamped with really high waves. That Mobile Bay is shallow and it can generate some really high waves real quickly in a storm. And people go out not thinking about it and they end up getting swamped and drowning out in a boating accident out in Mobile Bay because of the waves. So the wave heights are important and have a lot of applications. Okay. Now, y'all remember from pre-cal algebra that they talked to you about transformations or translations. They both of those words. How do I change the basic shape? Maybe I have a parabola and maybe I want to make it widen out or maybe go tighter, or maybe I want to shift it, translate it up so many units, or translate it down, or maybe I want to flip it over and have it reflect across the x-axis. Do y'all remember some of that stuff? Guess what? That's still true. All of that is still true in trig. So the basic concepts of how I can translate a file to get the basic shape to do something different, but it's still predictable what it's going to look like, it's still in play. So the concepts, and I've never heard anybody else say it this way, but I always think about it as How is it changing it vertically versus how is it changing it horizontally, right? And so the vertical changes always occur outside of the angle. So I can cause this to be moving up or down by adding or subtracting something to it vertically. I can also increase the amplitude outside of the angle. So that's a vertical change, changing the vertical amplitude. So what are some outside changes? And when I say outside, I mean outside of the inside where the X is. And that's how I would say it in pre-calc. Inside where the X is, when I change that, it changes it horizontally. But outside of that, it changes it vertically. And so for us, inside where the X is in the where the angle is. So let's identify first the things that we can do to affect it vertically. So going back to algebra, if I were to add a number to the outside of the sine function, I'm going to add a number or subtract a number. That is called a vertical translation, and it's going to shift it up or down. So if I were to say plus 2, and I called it D because it's right here, but you could just think it's your vertical translation. Plus 2 means I'm going to shift it up 2 units. So it just slides it up 2 units. If it said outside of the angle here, outside of the sine function, if it said subtract 4, it's going to take your basic sine curve and then slide it down 4 units. We're going to do some pictures here. We're going to look at it. But I wanted to talk about your vertical changes first. So here's your vertical change. This will slide it up or down, and it's when you add a number or subtract a number outside of the angle, outside of the sine. Now, there's another thing you can do to change the shape. This time now, this vertically changes the shape. So just like in algebra, if you multiply the front of the function by a number, you could stretch it or shrink it vertically. And for us, that's changing its amplitude. So let's say I wanted that wave to go up to 6 units and then down 6 units. I would put a 6. I would multiply the sine by 6, and it would cause the shape to go up higher and down lower. It would increase the amplitude. Now we put an absolute value there because going back to, again, to algebra, if you had the x squared graph, that's a parabola that faces up. What if I multiply the x squared by -1? It flips it and makes it go down, right? So that would be reflecting it over the x-axis. It's a downward reflection, or upward. It's going to reflect it vertically because it's outside of the function, not inside where the angle is. So multiplying by a negative will cause a vertical reflection. Now and that's what A is, the amplitude. Now, so they take the absolute value because the amplitude's always positive when you give an answer. You're not going to say the amplitude's a -2. It's always, the answer should always be positive. All right, now inside. There are 2 things you could do to the inside of the angle, but inside where the angle is affects a horizontal change. So one would be that I'm going to change the period. In other words, if I wanted to cause these all this to, like an accordion, you've seen how they are like a slinky, how you push it in and pull it out and slick and then pull it out. What if I wanted to compress this horizontally so that the 2 points are closer together, the 2 high points? Well, that would cause my period to I would have the same shape, but over a shorter distance. It would compress it horizontally. That's affecting the period. It would no longer be 2 pi. It would be shorter. I could also stretch it out horizontally, and it would increase the period, and it would take longer to do that to repeat itself. So how that is done is by multiplying the angle by a coefficient. So if the angle has a coefficient, it's changing the period. And we have a formula that's going to predict how it changes it. And it's the standard period divided by whatever the coefficient is. Now, there's one last thing we can do to this. And that is I can take it and shift it, slide it to the left or to the right. So I can slide it horizontally. And that is called a phase shift. And that is caused by adding or subtracting a number to the inside where the angle is. So this was just like in pre-cal, where maybe you wanted to shift it 2 units to the left, but in the inside it was reversed, right? So if I wanted to go 2 units left, I had to add 2 on the inside where the X was. If I wanted to go 5 units to the right, I would subtract 5 from the angle. But there's just, and we're going to get to this, it's just a little bit tricky though. If there's a coefficient, I have to factor that out to figure out what the true phase shift is. Now, I've had people say, I don't understand all these A, B, C's, and D's. It's just positional. It's just a way to give it a place and a name. So that if it's multiplied in the front of the sine, to the front of the sine, it's your A amplitude. If it's a number multiplied to the X on the inside, that changes your period. And D is if I add a number to the outside, that's a vertical translation. It's going to shift the graph up. And if I add or subtract a number C on the inside, it affects the phase shift of the graph. Okay, so what would these values be for my standard base graph y equals sine of x? We know the standard period is 2 pi. The phase shift, notice there's no number added on the inside there where the x is. The phase shift would be 0, so it's not going to shift it. There's no number added to the outside, so it doesn't have a vertical translation, so that's 0. Now the amplitude, the A, is the number that's right in front of the sine. And I'm like, I don't see a number in front of the sine, but it has an understood 1, an invisible 1. So my amplitude meant that my sine from the origin went up 1, and then it goes down 1. And it goes between a -1 and 1. But the amplitude, we say, is just 1. Goes from the x-axis up 1 unit. All right, so there's your base sine curve. Now, based upon this, I'm going to look at this function right here. And we could graph this. You could graph this if you wanted to. And actually, sometimes what people will do is they'll graph both. On the first y equals, they'll leave your basic sine curve, sine of x. And then on the next line down, on your y equals, on y sub 2, it'll put the new one up there so they can compare how does the new graph look compared to the original base graph. Did it move it up or down? Did it change the period? Did it increase or decrease the amplitude? Did it do any kind of reflection? But we can, without a calculator, figure out how this graph is going to change. This is why I'm saying at a lot of schools they don't let you use a calculator, because you can go through, if you remember this, you can know what to do. So let's first look at the number A. So in the place of the beginning part right there was the letter A. The A value here is a -2, right? Now, what is the amplitude? The absolute value of the A. So our amplitude is 2. That means the graph is going to go up to 2 and then down to a -2. So it stretched it vertically. All right, now let's keep going. The next one is the coefficient of the x. Well, what's the understood coefficient of the x? 1. So that means that the period is not changed. Nothing was multiplied to the x. And notice on the inside there is no c. Nothing was added or subtracted inside here where the x is. So it didn't change the period and it doesn't have a phase shift. But we did have one other thing done to this that's outside of your base graph, and that's this number here. This represents what? Up or down? D, your vertical translation. So this is going to take your standard base graph and cause it to shift up 3 units. So we do have a vertical translation of 3, which means up 3. But there was one more thing, and that's why I've got this in blue. The fact that it multiplied by a negative means it's going to reflect the answer over the x-axis. So when it would have, the base would have gone up, this one's going to go down. And where the base goes down, this goes up. So it just reflects it, mirror images it over the x-axis. So let's sketch this graph. So if I were going to take the base graph, first of all, the base graph goes up, but ours needs to go down because of this reflection. Now, normally the base graph only goes up to 1 and down to a -1, but because our amplitude got moved to change to be 2, it'll have an amplitude of 2 units. So it goes like down 2 and it goes up 2. And then one last thing, the base graph will shift up 3 units. So the sequence of the order that you do it, you can shift it up and then just keep. Now the period stayed the same, so it's still going to go just to 2 pi and then repeats the same shape. But we changed the amplitude to 2. We reflected it over the x-axis so it mirror images it, and we took the whole thing, and instead of the middle being at the x-axis, it shifted the whole thing up 3 units. So when you graphed it, now remember the curve will keep going. It'll keep going, but is that what your graph looked like when you graphed it on your calculator? Okay, so I know there's a lot of little nitpicking going on with this, but it's good to learn this. Now, the way the homework, it's going to ask you, like, what is the new period? And we didn't change the period, so the sine curve stayed 2 pi. And it'll say, what is the amplitude? Do not say a -2, because that's not the amplitude's always positive. You take the absolute value, and the amplitude would be 2. And it would say, what's the vertical translation? And you would say 3. All right, now we got another one. So this time we got this curve here, 4 sine 2x. So I'm going to compare it to my little thing here. And some parts of these are missing, like there's no D, right? I don't see anything added or subtracted, so we didn't get a D. C is what is added or subtracted inside where the X is, and I don't see anything added in there, so I don't have a C. So it looks like all I have is an A and a B. So my A is 4 and my B is 2. What does that affect? Well, the 4 affects your amplitude. So your amplitude is the absolute value of A, the absolute value 4. So my graph is going to go up 4 and down 4. So it increased the vertical amplitude. But it's also going to change the period because B is part of the calculation to change. We have a little formula that says, what is my new period going to be? My base period is 2 pi. So if I have a coefficient to the x, I put that in the denominator, and I say 2 pi over 2. And that's going to tell me what the new period is of this graph. 2 pi divided by 2, the 2's cancel out, and I get the period is pi. Now let's think about what that means. Normally, the graph goes up and then down and back over a distance of 2 pi. But now I'm going to do the same thing, but only over a distance of pi. That's half of what it was. So it's going to cause those waves to come closer together. So we had no phase shift, no vertical translation, but we have a new different period and a new amplitude. So the graph, the sine curve will still start. It'll start at the origin and it'll go up and down and back. But notice the amplitude says it's now going to go up to 4 and down to a -4. And I'm going to have to do that, all of that over a shorter width, a shorter horizontal distance. So I'm going to do all of that in just pi units instead of stretching it over 2 pi units. So if you were to look at your graph, those curves are going to curve real close together. Remember, this keeps going, but I'm just showing one repetition of the wave. The waves will be closer together and they will go up higher. Now, for you boaters, is that a good thing? For the waves to come close together and go up high? No. That's a good chance to get you tipping over if it goes up too high and they're too close together. If the waves are high but they're far apart, the crests are far apart, you have time to go up and then go down into the trough and come back up. But if they're real close together, you're trying to go up and then you're all of a sudden coming down and you're having to turn back up again. Yeah, this can be a dangerous thing. So close to get real close together waves, if you're talking about water, is not a good thing. All right, now we got another problem. So this would be one you would see for the homework, and they want you to tell about the amplitude, tell about the characteristics of this graph. How does this one differ from the one that is your base sine graph? Is the graph going to have a different amplitude or the same amplitude? So where do I look for amplitude? The number in front multiplied to the sine. Well, my base graph just says sine with an understood 1 in the front, and this graph has what? Just a understood 1. So the amplitude is the same. So it's only going to go up 1 and down 1. But what else is it going to change? Is it going to vertically translate it? Make it go, the whole thing shift up or down? No, there's no vertical translation. But I do have a change to the period, which we just talked about. but I also have a phase shift. So let's talk about how that works. So what's inside there, we've got to get it in the form of b parentheses x minus c. Or so in other words, I'm going to have to factor out the 2. I'm going to have to factor out the 2 so that I can figure out what is the true phase shift. And somebody says, why do I have to do that? And it's like, because that's the way the formula works. It's the best I can explain it. All right, so when I factor out 2, I mean I divide both of these by 2. And so here is my b, which changes the period. And this is the phase shift. Now notice the formula was a subtract formula. So this, we won't say negative 2 pi, we'll just say 2 pi. So it has a phase shift of 2 pi. So that means it's going to shift it 2 pi units to the right. And it's going to change the period. The phase shift is a horizontal shift to the right. The period, the new period, we take the standard period 2 pi and divide it by that coefficient of x, which was 2, cancel out the 2's, and we got pi. So basically, this goes up 1 and down 1, but it shifted it, and then it shifted it to pi, but by shifting it to pi, it still looks the same. Most of the time, your phase shift might be just something less, like pi over 2. Yes, ma'am?
How did you get the 2 pi for the phase shift?
Inside here, the question is, how did I get 2 pi for the phase shift? Inside here, the parentheses where the angle is, was 2x minus 4 pi. I have to factor out the coefficient to figure out what's the true. The phase shift wouldn't have been 4 pi. It would have been, so I factor out the 2. It's kind of like getting the greatest common factor out, but it's really, you're just factoring out whatever is here. So I divide both of these by 2. That tells me what goes on the inside. That undoes the distributed property. I should be able to distribute the 2 back and get what I started with if I did the division correctly. Now the true, because it's a subtraction formula, the true phase shift is the opposite of this number here. And it kind of goes back to when you were studying, this is the same thing when you were studying how far does it go to the right or to the left, how many units. That was a phase shift, really. They didn't use those words, but it was a horizontal phase shift. So we always do the opposite sign. So if this ends up being subtract 2 pi, we're going to say it's a positive 2 pi. And that's how we get it. I know this is kind of dry stuff here. And I understand that, but you're being able to understand that, particularly if you're transferring where somebody doesn't let you use the graphing calculator, but you got to graph these things because you're going to be working with and you got to do other stuff with it. It's really important that I get an idea of what is going on here. Now, this is a basic one here. All they did is, well, they did 2 things, but it only affects it because it's multiplied to the outside of the sine and not inside with the angle. It only affects the graph vertically. Doesn't affect the graph at all horizontally. So it doesn't affect my phase shift because notice inside here where the angle is, it's just x. So there's no phase shift, there's no period, there's nothing added or subtracted, so there's no vertical translation, so it's still centered over around the x-axis. But the negative did something. What does the negative do? Cause it to reflect. And the positive, and if you take the absolute value of that, it gives you your new amplitude. So what this graph did is it reflected it, the negative reflected it over the x-axis, so it goes down and then up. reverse of what it normally does. But it changed the height of each curve. So the amplitude is the height. It goes up 2 units. It goes down 2 units. The amplitude is 2. So do you see how to come up with these answers they're going to ask you? They'll give you the equation and ask you to tell about it. Now, the cosine curve, the nice thing about the cosine is it's just like the sine. The same rules, the same words. So for cosine, you still have the words phase shift and vertical translation and amplitude. And in fact, I'm going to go forward and show you another graph so that you can really, and I'll come back to that. The only difference between the sine and the cosine is that one is a phase shift over, horizontal phase shift from the other. So while the red was the sine graph, goes up to 1, down to 1, it has a phase, has a period of 2 pi, the cosine is the same. It has the base cosine goes up to 1 and down to -1. Don't let that other thing, but it's showing the half ones in between. It goes up to 1 and down to -1. And it's a continuous curve. They look just alike. They're just not tracking, not tracking through the same ordered pairs. So while the sine goes through the origin, notice that the cosine is up here at 1 when the angle is 0. Now remember we talked about the sine and cosine, one being a even function and the other was an odd function. The definition of an even function is that it is symmetrical to the y-axis. What do you notice about the cosine graph in green? It is what? Symmetrical to the y-axis. So that's why the even, when we were trying to do negative angles and we were looking at even and odd functions, I said cosine was an even function. It is symmetrical to the y-axis. And I said that the sine function was odd. And an odd function has odd symmetry to the y-axis. So like if this was a positive value, then this one, if you have the negative of the x, it is the negative of the y. So it says times -1 to both of them. So it has what is called odd symmetry to the y-axis. And that's where that came in. So the rules for the sine and cosine are exactly the same. They just aren't at the same points at the same time. So, but the distance, the phase shift is still 2 pi. The magnitude is still 1. Now, how did they get the cosine curve? They took the x values of the angle as opposed to the y values. So when you were looking at those terminal points, it's going to take all the x values and graph them. And so the domain is all real numbers. The range is a -1 to a +1. Standard period is 2 pi. The y-intercept is different. The y-intercept, it crosses the y-axis at the point where y is 1. And the x-intercepts are different. Notice it crosses the x-axis at those halfway numbers, those half numbers. So like at pi over 2, 3 pi over 2, those are numbers like 1/2, 1.5, 2.5, 3.5, 4.5. It's crossing at the halfway points. But the rules for finding the magnitude and the period, if you can do it for the sine, you can do it for the cosine. It's just a knowing about the graph is does, it's shifted over. It actually has a phase shift distance of pi over 2. So like the cosine is pi over 2 shifted to the left, a horizontal phase shift of pi over 2 from the sine. So that's why they're really going to be, in everything we studied, the sine and cosine are really closely related. They're like sister graphs. I mean, very similar. They just don't track through the same points at the same time. Okay, so what if I had a -2 times the cosine? The angle is 2/3 x, and on the outside it has a +1. So this graph has a lot going on, doesn't it? So could we look at this graph and figure out what the equation would be? So that's a little harder if they give you a graph and say, figure out which one is the best graph, the equation that matches this. Well, why would I automatically think this would probably be better with a cosine than a sine? Think about when you're at the origin or you're on the y-axis. The sine function was crossing through the origin, right? So it was half one. When you hit the origin, I'm going to show you that. I'll come right back to this. The sine curve, even if I shift it up or down, the y-axis is splitting it when it's either on the way up or if it's reflected on the way down. So if the y-axis is splitting it between the low and the high, that's a sine curve. Now, if, look at what the cosine does. Where is the graph, the y-axis doing? It's hitting it at the top of the curve. If it reflected it, the y-axis would be hitting it at the bottom of the curve. So when I go to look at a graph and I've given a bunch of equations, I say, which equation best matches the graph? The very first thing I'm going to look at is, what is the y-axis in relation to the curve? Is it at the bottom of a valley or at the top of the hill? If so, if that's where the y-axis hits the graph, that's a cosine curve. But if the y-axis is hitting it right in the middle here, or right in the middle here, that's a sine curve. So right from the start, there I can automatically, on a multiple choice test, say, no, it couldn't be it's not a sine. So now we know it's going to be a cosine. We know that it normally, let's start with the amplitude. The amplitude is always, if you put a horizontal line through the middle of the graph, such that half of it goes up and half of it comes down. If you count these blocks from the middle up, it should be the same as the middle down. That's your amplitude. So this amplitude, this is a 1, 2, 3. We can see the amplitude is 2. So from the middle up and the middle down, a line that bisects this thing horizontally in half, the amplitude is 2. But it should be at the top of the hill, not at the bottom of the hill. The y-axis should be at the top of the hill. So this thing got reflected. So my amplitude has got to be what's in front here is an amplitude of 2, and a negative sign says it got reflected. Now, what else changed? Well, notice the middle of it is not the x-axis. So this thing got what? Shifted. How? Shifted. It has a vertical translation of 1 unit. So I'm going to add 1 to the outside. Now, the last thing is, was the, it didn't have a phase shift, but did it change the period? And it did, because the period, here's the y-axis and here's 2 pi. If it's the same phase, the same period, at 2 pi, I should be back at the bottom of the hill. If the y-axis is at the bottom of the hill, then at 2 pi, it should be back at the bottom of the hill. But it's not. So it has increased the period. So how did it increase its period? Well, increased it to where it's back at the hill, not at 2 pi, but at 3 pi. So it changed it from 2 pi to 3 pi. So let's figure out what was done here. So remember how we find the new period. That's the coefficient, the b, that's in front of the x. That's multiplied to the x. So I'm going to take 2 pi and I'm going to divide it. Normally, I would divide that by b. This is the formula, 2 pi divided by b. But now I'm trying to figure out what the new phase shift is because I'm trying to come up with the equation. So I set the 2 pi over b, the equation to find the new period, to what this graph's period is. So the distance from the bottom to the bottom was 3 pi. So I set it equal to 3 pi. Now I'm going to solve this for b. So I can do my cross products, or I can multiply both sides by b, and I end up with 3 pi b equals 2 pi. Solving for b, so there's several ways you could do that. You could put the 3 pi over 1 and do cross products, or I can just multiply both sides of the equation by b. When I multiply this side, the b's cancel out, and I get the 3b over here. So 3b pi equals 2 pi. Now solving for b, I divide both sides by 3 pi. The pi's cancel out, and this is the b. This is b, the coefficient of the x. So it's 2/3 x. I know this is getting into formulas and all, but hey, y'all, you don't find history majors usually taking trig. Yes, ma'am.
I'm so confused where you get the 3 pi from.
Okay. When I was looking at the graph here, it's hard to see it, but one period is from the bottom of this to the bottom of this right here. So if I'm reading this, it kind of got lobbed off. But if you're reading this, this is pi over 2 pi, 3 pi over 2, 2 pi. Hard to read it, but it would be, well, let's just read it this way. Every 2 is pi. So this is 1 pi, 2 pi, 3 pi. I'm back at the bottom at 3 pi. So and I went from the origin because it's easier to start at 0. So the distance from the bottom to the bottom, because the bottom was where it was on the y-axis with this one, is 3 pi, a distance of 3 pi. So my standard period is only 2 pi, but this one got enlarged to be 3 pi. So to try to figure out the coefficient, I take my formula. This is the formula for finding the new period. I set my formula equal to what I tell from the graph that the period is, which is 3 pi. And then I just use my algebra skills to solve for b, and that tells me what the coefficient of the x is. Then what you can do is you can take your calculator and put this in the calculator and see, does it match the graph that I'm seeing here? Now, some people on a multiple choice test will just put all of these in the graph and try to pair, but you really got to be able to notice little small differences. Now, the problem with the homework, it's not multiple, some of the questions are multiple choice, but a lot of them are not. And they would say, what is the face, what is the news, what is the equation that best match? Or they would look at this, another way they might would do the questions that they might would just ask you these things. What is the amplitude? What is the period? And you just count to figure out what the period is. What's the vertical translation? Shifted it up one. And then they might say, now what would be an equation that matches that? Okay. I know this is harder. Anyway, well, that takes us to the end of the lesson. Always good to end on a high note like this. But it takes us to the end of the lesson. And that actually, we've got 4 other trig functions to look at. And there, 2 of those are alike and 2 other of those are alike, but they're not like the sine and cosine. So of the 6 trig functions, sine and cosine are alike, tangent and cotangent are alike, secant and cosecant are alike. So anyway, y'all have a good weekend. I'm so glad that you came. You can always email me questions or ask questions in class. You can ask. You don't have to, you can, in the virtual world, you can ask me questions too.